What type of figure is like a lost parrot? A polygon! No, it's not really. But because we're doing 6-1, let's look at actually what a polygon is. As a reminder, a polygon is a closed figure, so it's a shape formed by 3 or more segments that intersect at their endpoints. We name a polygon by the number of sides it has, and these names will all seem familiar to you, and you can see that in the table below. And looking through this list, most of these names should sound familiar. I know you've heard triangle, quadrilateral, probably pentagon, even octagon. You've heard most of these names. Now, if you notice, down here it's the n, number of sides is n, and it's called an n-gon. What that basically means is that after the number 12, if a polygon has more than 12 sides, we just call it an n-gon, whatever, how many sides it has. So if a polygon has 17 sides, you simply just call it a 17-gon. Beyond giving them names such as quadrilateral or pentagon, we also classify polygons. And how do we do it? We have 3 terms that we're going to be using. That first term is a regular polygon. A regular polygon is a polygon with all sides and angles congruent. You've seen these all the time. Some common examples would be a square or a stop sign. The second term we have is a concave polygon. It's a polygon that has a section that points inward. Notice, try to make the connection between the word inward and cave. You know, a cave as normal, where you go in, you can go into a cave, and therefore a concave polygon points inward. An example drawing of this would be the following quadrilateral. Notice that every single part seems to, point outward, except right here. Because this points inward, we call this a concave quadrilateral. And of course, this definition of concave polygon is not very mathematical. It's just what makes sense in common words. And lastly, the last term that we use is convex polygon. It is a polygon that is simply not concave. Most shapes that you see, most polygons you see, are convex. An example of this could be the following quadrilateral. Notice the differences between the first one I drew. They both have 4 sides, so they both are quadrilaterals, but the top one points in right there, and there's no part of the bottom shape that points in, and so we call it convex. Oftentimes you want to know how many degrees are inside of a certain polygon. What's the sum of the interior angles? And what I said was to think of triangles. What I mean by that is, if we look at a triangle, I can draw any triangle I want. But this triangle here, think about all of the interior angles. This angle here, this one down there, and this one up there. Think about what all of these have in common, or the relationship between them. They all add up to 180. So whatever these actual measures are, no matter what, they add to 180. So you need to remember that there's 180 degrees in a triangle. So why is that helpful? Well, let's think of a situation where we want to find out how many degrees are in, let's say, this irregular pentagon. I drew a pentagon because 1, 2, 3, 4, 5. There are 5 sides there, so we call it a pentagon. So how many degrees are in this? Think of triangles. Try to divide this pentagon up into a bunch of triangles. So let's talk about just one vertex. One, corner of the pentagon. What we're going to do is we're going to draw diagonals across this pentagon, all stemming from one vertex. I just chose the leftmost one, but we're going to draw diagonals straight across. One's there, and one's there. Notice I didn't draw a diagonal from our vertex straight up because we already have that segment connected. I was just trying to make the segments to each point that we were not touching already. And now, how many triangles do we have? we have one triangle, two triangle, and three triangles. Meaning that if we remember again the 180 in a triangle, we have 180 degrees in this top triangle, 180 degrees in this triangle, and 180 degrees in this triangle. Meaning in this pentagon, and any pentagon for that matter, a pentagon is going to have 3, because of 3 triangles, times 180. Meaning there's going to be 540 degrees in any pentagon. So using that idea, what we want to do is find the number of degrees in a 101 gon. What that is a polygon with 101 sides. Well, in my opinion, drawing that would take a very long time, and then dividing that up into triangles would take even longer. How can we go about this then? Luckily, we have a theorem that's going to help out quite nicely here. And where this theorem comes from is that all shapes, or I should say all polygons, have n minus 2 triangles in them. What that means is that our pentagon had 5 minus 2, which is equal to 3. It had 3 triangles, so that we multiplied it by 3 times 360. So anyway, what our theorem actually says is the sum of the interior angles of a convex polygon with n sides is n minus 2 times 180. So what that means is this problem that we have, this example, actually gets quite easy. So we ask, how many sides does a 101 gon have? 101 gon has 101 sides, as we talked about before. So now, what we need to do to find the sum of the interior angles, n minus 2 times 180, which means we're going to do 101 minus 2 times 180, which is 99 times 180. And what this turns out to be is 35,640 degrees. So kind of how a triangle, all the angles add up to 180. Inside of a 101 gon, all the angles add up to 35,640. And so determining in a polygon how many what the interior angles add up to, it's quite easy. You just multiply it by n minus 2 times 180. Here's another example for us. We want to find the measure of each interior angle of a regular decagon. This question is similar to the other one, but now instead of just the sum, we want to take it a step further and find the measure of each angle. So what we first need to do is, let's think, decagon. How many sides is in a decagon? Well, you can look back at your table and you'll realize that this is 10 sides. 10 sides to this shape. So now we ask, what is the sum of all interior angles? This is what we used that theorem before, and we did the n minus 2 times 180. So meaning we're going to do 10 minus 2 times 180, which is the same as 8 times 180. And what does that turn out to be? 8 times 180 gives us 1,440 degrees. Alright, now if the question just simply said, what is the sum, then we would be done. But it says find the measure of each interior angle. So to do this, to find the measure of each interior angle, we need to take the total sum, and we need to divide this by the number of angles. So in this specific case, because we are talking about a decagon, we use that 1440, which we just found above, because this was the sum, and we're going to divide it by 10 because there's 10 angles in a decagon. This gives you 144 degrees. What that means is that in this specific shape, in a regular decagon, every single angle is 144 degrees. Let's go look at that pentagon from before. What we were trying to do before was find the angle measures of all of these angles here. Now, as a reminder, what we call each of these angles is an interior angle. And so every one that we were looking for before was the interior angle. And that's when we do the n-2 thing times the 180. But what happens if we want to look at exterior angles? So as a reminder what these would be, I'm going to go ahead and extend all of our sides of this pentagon. Going ahead and extending, and after we've extended these sides, what we're asking, or what we're discussing, are this angle here. How about this one there? Here, here, and here. Notice they're outside of the shape. They're on the exterior. And so we want to know, what is the sum of all of these blue angles? What do all of these blue angles add up to? Is there an easy way to know it? And actually, yes, there's a very easy way to know. We have theorem 6-1-2, which is the polygon exterior angle theorem. What it says is that the sum of the exterior angles of a convex polygon is 360. What that means is that all of these blue angles that I marked here, they all add up to 360 degrees, always. We could be talking about that 101 we were talking about, a triangle. Any convex polygon, these will add up to 360 degrees. Each angle is not 360, but they add up to 360 always. And our last example for the day is to find the value of r in polygon JKLM. Now, I've not made a point of it earlier, but we named polygons similar to triangles to where every single vertex we classify. So J, K, then L, then M. So the first question to answering this is, what kind of polygon is it? So we say this one has 4 sides, so we should know what type of it is. It is a quadrilateral, because that's a 4-sided polygon, quadrilateral. And then we have the question, we're looking for R. So is R on the inside or the outside of this polygon? And so we're looking at the R, and let's see, here's outside, 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 outside. All of these are on the outside. And so actually, this question here of the 4 sides quadrilateral, it doesn't matter in this specific case. If they were on the inside, it would. But because it's the outside, we can use that theorem 6-1-2. And all of these exterior angles add up to 360. So what we can say is 5r plus 4r plus 8r plus 7r is equal to 360. Now it is important to note, remember, if these were on the inside, then you would not set it equal to 360. Because the interior angles don't add to 360. The angles inside don't add to 360. The outside angles add to 360. So continuing this, adding up the r's, we get 24r is equal to 360. And then we do 360 divided by 24, which gives you r is equal to 15. And now we are done.